Donc là, je stream. Bah écoute,
Okay, so I have to start the Zoom link, right?
I'm inside, but I don't know if I'm the...
Well, I don't think so. I was just waiting for host, right? So when I start it, I can let you in.
Ah oui, il est quand même admin.
Ah, it's okay, I was admin, okay. But why I see these rooms? No.
Oh, it's just a symbol.
Host sign in. Okay. But you need a computer.
Bon, bah, je peux repartir.
But apparently, no, the problem last time was that where yes, in room Zixon, in room Cloud Block, the Zoom was outdated.
Ah, là-bas aussi?
No, there was updated. Here I didn't do anything.
Oui, là c'est pas à jour.
Non, dans l'amphibloc, c'était pas à jour.
C'est pas à jour, d'accord. Mais
ici, ça a marché, n'a pas
marche.
râlé. Mais il faut penser à chaque fois la faire passer la mise à jour de Zoom, sinon il te bloque.
No, I let you in.
Sono admin. Ah, no, questo qua. Ma quello sei tu che devi decidere che io divento grosso o piccolo.
Ma quello lo fanno i partecipanti, no?
Ah, ok. Ah, sì, qua, view.
Poi you can do, I think, pin video if you right click here.
Ok. Ok, questo lo prendo. No, lo metto là. Questo lo prendo o lo metto là. Ah, no, però devo vedere se sto... Est-ce qu'il y a les sons? Ah no, allora, video yes, but audio no. Join audio. Join computer audio. Down. C'est bon? Ok, questo lo posso chiudere, no?
And do you know, by the way, so usually when you go and you see the video in the Zoom, I see it mirrored.
From your side.
Yes.
You
Is
have
that
to,
normal?
yes, but because by default
On this
Zoom,
computer, yeah.
on this computer you have to go to preferences.
Yes, but I don't know where there are preferences, but yes, in preferences you can choose.
Okay.
But I don't know how to go in preferences.
Okay, because I wanted to make sure that people.
Yeah, the people
right.
yes.
Because it doesn't matter for me, of course, because I have a speaker here.
I invented the title. I didn't know the title.
Okay, I think we're.
So we are streaming and we are on YouTube. Streaming public, so everybody sees it.
Okay. We're not planning to insult anyone.
Scelto il titolo? Scelto il titolo. Gli ho appena detto, me lo sono inventato, ci voleva un titolo.
Chi vuoi che l'avesse scelto?
Comunque attualmente...
Peccato subito che l'aveva scelto. Peccato subito che l'aveva scelto.
Sì, chi è che...
Scusa, se vuoi il titolo, se vuoi lo cambio, non c'è problema. Ho anche messo lo speaker, avevo un dubbio se era N o Nberg o Mberg. Ecco la N.
No, così è giusto.
È come Werner. No, solo che... Sì, solo che è ancora peggio che è SS. Cioè, avevo la versione di steroidi...
Boh, poi accendo la luce. 468 CO2.
In realtà, Carlo, si è visto o no? Perché io
In realtà vai.
Welcome everybody. So this is the second and last mini lecture by Carlo on BMS group. And yeah, thanks, Carlo. Go ahead.
Yeah, thanks, Brando. So, yeah, let me start with the second sort of installment of this mini course, introductory mini course on BMS symmetries and, let's say, related topics. And so today, this is the schematic outline for today's talk. And essentially, as you can see, the idea is to start with some topics that are a bit orthogonal to the ones that we discussed last time. So we start very, as I said, introductory level, just by reviewing a bit the soft graviton theorem and how this predicts the experimentation of soft graviton emissions and closely related topics on IR divergences. And then we will find sort of a connection between the topics discussed last time when we will come to the memory effect, which we see essentially arises as a Fourier transform of the soft graviton theorem, and we will review how this in a sense, the memory itself can be seen as the action of a BMS translation, thus sort of closing this triangle, which has the soft gravity on the BMS symmetries and the memory at its corners. And then finally, if time permits, maybe we'll discuss something about how this soft gravity theorem can be also used to predict some other observables, not just the memory, but also some properties in particular of soft spectra, like the zero frequency limit of the energy emission spectrum and the static portion of the angular momentum loss for a binary system. So yeah, let me begin very broadly just by referring something that we're all very familiar with. Let's take some amplitude that has some external states that I will label some P1, P2, the momenta. Let's say M, small m incoming ones, and then M plus 1, Pn minus 1, Pm. And suppose we are interested in an amplitude which differs by this. So the details of these particles are not really relevant. They are just particles that have some momentum, may have additional quantum numbers like spin, etc. But it will not be relevant for today's discussion. And suppose we are interested in the process in which, together with these particles, there is the additional emission of a very soft graviton. So this K is the momentum of graviton, and in the limit very small k, this amplitude factorizes into some factor that depends on the momentum and in general on the polarization. So I will write with some free indices of this graviton times the amplitude does not have the soft emission. And this is a well-known result by Weinberg, of course. Some outstanding papers that go back to the 60s. And the form of this soft factor is the following. Well, and okay, I'm taking this convention according to which all momenta are regarded as formally outgoing. So in particular, P1, P2, etc. are minus the physical momentum of the incoming particles. So as I said, this formula is very general. It only depends on the momenta of the other particles, sometimes called the hard particles, as opposed to the soft graviton. In particular, the other particles might have spins or tangents, deformations, or so they don't matter, only the momentum. So just as a quick way of checking that I didn't make mistakes, one can check this an example. So for minimally coupled massive scalar, this is for instance the vertex that one can derive easily from a Lagrangian. Minus eta mu, equals P prime, minus m squared. So this will be the vertex for something like this. And well, Weinberg's argument is that since the graviton is very soft, the dominant contribution comes from diagrams in which attach it to the external legs of the, let's say, parent, like this. So this is PA, you attach it in this way, K. For me, everything is outgoing, so this is going to be PA plus K. And therefore, the other ingredient that we need is the propagator, which is just minus I. Squared plus m squared, let's say, for each A. So, well, the amplitude is very simple. You have the full amplitude, involving only the hard particles multiplied by the propagator and by the vertex. So this gives a factor minus I square root of h by g. And then, since here I would have to plug PA and PA plus K, right? With the opposite sign, to be precise. But since I'm working to leading order for small k, we can neglect the shift by K. So this is n mu PA nu, and twice that, because this could become effectively the same. And the other term is also negligible, this guy, because it becomes again proportional to K. The denominator here comes from the important bit. Well, one really wants, there is also this minus I epsilon. And you see when expanding this, p squared cancels with m squared, so you only get 2 pa.k. So I didn't make mistakes. You should really feel this factor that I wrote. Mu divided by pa minus I0. And here it means that essentially the amplitude diverge is like 1 over the frequency, right, of the soft graph. So this is why it's also called the 1 over omega soft theorem sometimes. Very good. So then the next question would be, well, what if you have more than one graviton? Well, the answer is eventually very simple. So suppose I have two of these guys here. Well, in this case, the formula is that you just have the product. So let me say this is mu1, this is mu2 with omega k1 and k2, and this is just w mu1, k1, mu2, k2 times the usual amplitude with only the hard part. And somehow the proof proceeds in a similar way, but well, of course, when the two momenta, the two gravitons are attached to different lines, the same argument follows. The only tricky bit is that when you have two gravitons attached to the same line, right? Because then it's not clear that the same calculation goes through. But then, well, the key point somehow of the argument is that if you compare whatever, of course, you have to sum over all possible ways of attaching these lines. So in particular, you should attach again to the eighth line, let's say k1 and k2, but also k2 and k1.
Are you assuming a hierarchy between k1 and k2?
No, they are generically of the same order. That's why, in fact, you should include both contributions. So basically, you can apply the same argument, and here you have q1 plus k1, and then q1 plus k1 plus k2. And similarly with k2 replacing k1. So the same argument tells us that, let me just focus on this denominator, because the rest, of course, does not depend on k. Here we would get 1 divided by pa dot k1 from here, and here 1 over pa dot k1 plus k2. But from the other one, we would get 1 over pa dot k2 divided by 1. And now, as you can see, by summing these two, they reproduce precisely the product of the two. So they do factorize, right? Because when you sum, you have the sum of the two in the numerator, which cancels precisely the denominators, and then the two denominators are left are only two units. So in fact, it's a very nice exercise that you can work out to show that this pattern is in fact general and works for.
Sorry, maybe a naive question, but could you in principle have the contribution which is like attaching one graviton line on the other graviton line?
Yeah, that's a very good point. This would be suppressed because then you would have some k also in the numerator, right? But it's a very good point. Somehow, morally, this is related to. I mean, we will see that eventually. Just to anticipate a bit, one of the conclusions will be that these soft gravitons attached to the external light actually Fourier transform to the memory effect. More precisely, they Fourier transform to something called the linear memory effect, which is associated with the fact that particles deflect. And so in this sum over here, the fact that the p after the scattering are different from the p's before the scattering means that this factor is non-trivial and gives this memory effect. Gravitons attached to other gravitons would be called sometimes the nonlinear memory effect, which is sourced by, instead of being sourced by the hard part, because it's sourced by other gravitons.
I have two questions. Is this a tree level or?
Okay, this yeah, very good. This proof seems very simple, and naively one can think there are many ways to to find loopholes, etc. And in fact, one particular branch of literature that has to do with higher spins has studied this result in great detail, and eventually it seems that this result is is true for any loop order.
Okay.
And also for generic spins, as I mentioned, I think there are some counterexamples one can find with higher spins field, but this is the only loophole that I'm vaguely aware of. So no, this is general.
And also, if you are at tree level, I don't understand in the first example when the graviton is attached to external line. What about if it is attached to some internal line with some sum of external momenta?
No, that's okay. The naive argument, which I think is the one that Weinberg used and apparently eventually is correct, is that if P wouldn't be on shell, then you wouldn't get this pole because there wouldn't be the cancellation between P squared and M squared.
Okay.
Just very naively, right? If you attach inside, particles are off shell. Of course, you may wonder, what if you attach it inside a unitarity cut, for instance, right? Because some particles can go on shell inside amplitudes when you have loops. But it turns out that they actually all cancel out this contribution. So Weinberg was right. Very good. So yeah, as I mentioned, this pattern is completely general, and you can generalize this formula in a straightforward way to any number of emissions, just by this is the R emission, and you can have as many as you want. This is the formula. So there is a nice combinatoric identity that you can work out by induction that proves that this identity generalizes to n factors. When I was spoiled last time because I had so many blackboards. Erase the previous ones instead. So now we understand how soft emissions work, and since we are, since Brando asked, and it's a very closely related topic, I thought I should mention also how the closely related topic of exponentiation of infrared divergences work, and then to touch upon the very well known conclusion, but physically very important conclusion that, as we will see, infrared divergences cancel out in observables against integrals of these soft emissions. So now suppose that instead of having just emissions, I want to consider effect of soft gravitons that are virtual, are infrared but virtual. Take for instance something like this. So very schematically, this means that there is some graviton loop inside whatever this bubble, this blob is, in which one soft graviton becomes very soft. One soft graviton becomes very soft. And okay, Weinberg didn't stop there, and also consider n soft gravitons. So for n, so adding, let's say, n virtual IR gravitons. What does it mean? Well, it means that you should multiply by two of this factor and glue them together onto themselves, right? And then you have to be careful about the combinatory of what you're doing. So I introduced a 1 over n factorial because I will label these virtual gravitons by some names, k1, k2, kn, but this is completely arbitrary. So, and then you have to integrate. Integral movement, and then we have this propagator that we had also that connect the two lines to one to the other. And then there is this product of two of these soft factors, over n and n, h by g, and then they can be glued together either with, saturating with physical polarizations, or since, in fact, I should have said that this factor there is this factor is gauge invariant, right? In the sense that this is zero by momentum conservation of the background process, because you would get sum over A of PA is equal to 0. So that doesn't matter. We can saturate, for instance, with the structure appearing in the numerator of the Donder propagator, say. So this is the result. Aha, n squared and m squared divided by two of these guys, right? Pn dot k minus I0. And then there is another subtlety, which is here, as I was saying, everything was regarded as outgoing, but of course now I have to be careful because one of the two must be incoming, so here comes a minus sign. And then there is also a 1/2 that is due to the fact that, well, it's completely up to me whether I decide that this runs counterclockwise or clockwise. And here, yeah, sorry, just to reiterate this external length. Yeah, Donna.
Tricky question. What about the case n equals m?
Very good. Let me come back to that, because actually in the paper, I think in the paper Weinberg is a bit nonchalant about that, but then he comes back to this issue in the book. So in fact, together with the references, I should have also added the reference to book number 2, I think, with the series Quantum Field Theory. And well, as we will see, essentially the thing is that you should also put that, but neglect the imaginary parts that come from that. So let me come back to this maybe when I write down the final formula. So yeah, by the way, let me mention that we are discussing this for gravitons. We all love gravity, but exactly the same discussion holds for, say, photons or infrared photons. I think that's the case that Weinberg focuses on in the book, and also for scalars. So that's completely, well, exactly the same. So very well. If this is okay, then okay. Of course, we will have to sum overall insertions of n IR gravitons, so 1, 2, 3, etc., etc. And as you can see, this thing is reconstructs the exponential series. So we will get some, I think I call it exponential of some w. And so more precisely, we think that the amplitude for this original process that we call collectively alpha and beta, the initial and final state, for the alpha to beta amplitude is equal to e to the w times an infrared finite remainder. And this w is, well, written down in the following form in order to isolate the integral I will use. 8 by z divided by 2 4 5 squared sum of n m, and produce some shorthand n half n squared, and some integral to be written down shortly. This sigma, well, I just introduced some notation that will be convenient for later. Let me define a symbol eta n, which is positive if the particle is outgoing and negative if the particle is incoming, and define, let's say, the true momenta of the particles, which are this and this sigma in some invariant divided by their masses. And okay, defining this way, they are. Okay, finally, so our task is to calculate this integral here that I haven't really written down yet. Okay. One thing that I hadn't talked about is that, of course, here we are just picking up the infrared divergence, and this you can see essentially by naked eye. Sorry, this should be L. Apologies for that. And well, because this goes like, well, L squared, so L to the fourth in the measure. So this is going to be infrared divergent. But of course, we cannot integrate over all L because this form is only attained for L that are small. So we need to put some cutoff, which I call omega star. So that's why the integral we are actually considering it.
Another cutoff, don't you have already? I cannot see.
Sorry?
In the measure we have for minus 12.
Yeah, so exactly, good, thanks. So this we're going slightly away from the equal 4 in order to obtain the infrared divergence. Yeah. But we want to calculate it, so we'll get something that was like 1 over epsilon in the end. Instead, we want to put this cutoff, omega star, which is a UV cutoff, if you want, in order to isolate this contribution from the soft gravity, right? in principle, the gravity will run in loop with any end, but the integral will be more complicated. So that's the game. You isolate, you extract the portion of the integration which comes from the infrared gravitons, and they get this form. Yeah. Very good. So this is the integral that we calculate, and that essentially Heissenberg calculated in this paper.
So the point you're making is if you didn't have the thing, you just get 0 because the scales are very.
Another way to see that is that if you don't put this cutoff, this is a scaleless integral, zero identical integral. But that's our fault, right? Because the integral will not be that in the reg. We can approximate it in this way only by restricting to L, which are very small, and that's why we have to put this cutoff, right? So in fact, Heissenberg uses 2 cutoffs because he didn't use the reg at the time. He used a UV cutoff, which is what I'm calling omega star, and another ER cutoff, which will size the infrared divergence that we are after. Instead, here I'm using this sort of mixed approach.
You can also put in a photon mass or something, right?
Yeah, that's also something you can do. In fact, I think maybe he did that instead of using 2 cutoffs. Maybe he put a fake mass and a UV cutoff. It's also possible. So yeah, the result of the integral, let me not do that in front of you on air right now because it will not be very illuminating, is the following. There is some Markov and minus I5. Let me define this symbol that goes back to the question by Donna earlier on. So the delta is, let's say, delta eta m. So it's something that is only there if the particles are all both incoming or all both outgoing. So this means, for instance, for a 2-to-2 process, this would be here for this, but not for something like this. And is not there, so if n is different from n, and is 0 if n is equal to 1. And it's also 0 otherwise, right? So coming back to the question by Donald, there is a contribution to the real part of this f that comes from when the graviton is attached to the same line, something like this, right? That's what you had in mind, I guess. And then okay, somehow we are a bit beyond what we can actually describe as scattering up, which is the field now, right? Because this would be a non-shell line before the emission and after the reabsorption, so this would be again on-shell. So formally this diagram is ill-defined, right? But Heissenberg showed then in the book that if you go through the renormalization in the proper way of the external legs, introducing the truncation of the external legs, which are to be dressed. So this is of course a correction to the effective propagator. Then you will find the exact same result as the one to get by this trick. So another way to see is that if n is equal to m, this imaginary part will be infinite, right? Because sigma and n is exactly 1, and therefore you get you will get 1 over 0. So you shouldn't put it there. And the final result is well, this w. And then sum. And then, okay, the sought after infrared divergence appears either as 0 integral from 0 to omega star, or if you prefer, as minus omega star to the 2x divided by 2x. So hopefully this should clarify the 2 issues that were raised earlier in the discussion. Indeed, we need the cutoff, otherwise this integral will be scaleless. This is enough for us to isolate this ER divergence as promised, but of course we have to pay the price that we don't know the full result. I mean, we only know it for the integrals up to this cutoff omega star. But the important point is that if you dress, I mean, if you multiply, let's say, if you have an amplitude, you multiply it by e to the minus this w, you will get an infrared finite amplitude. This is the well, important take-home message. So very quickly, let me compare what happens here with well, with what happens if one considers now the emissions of real clusters, right? And we'll be able to check the cancellation that I was anticipating. Maybe I can already start here. So suppose now we are interested in an amplitude that, I mean, we go back to the previous case, right? And emissions. As we already said, this well, this attains this factorized formula which have n soft factors times the amplitude without any emission. So this means, again, let me call this alpha beta, but then include also an n to remind ourselves that this is now an amplitude with also n soft gravitons in the final state, right? So this is well, the emission rate for n, the differential emission rate for n soft gravitons on top of the process alpha beta will be given by the absolute value squared times the phase space measured, collectively by the number. And well, explicitly this is the mu product on all your soft gravitons, 1 over n factorial again due to the labeling which is arbitrary, and then the 4 minus VR, 4, and then the delta that put them on. So now well, we can use the result that I presented earlier. So again, that this is actually a factorized contribution to leading order in the soft limit. If you are interested in very soft emissions, this will be A alpha beta times n of these soft factors. So in particular for gravity, this d gamma, so that unfortunately this does not. For n gravitons will be 1 over n factorial from 1 to n. And then, okay, the game is that we should again glue together, right? I mean, some of the physical over the physical polarization, or glue together the indices of the soft factors, right? So we get precisely the same factor that we had earlier, essentially. After integrating, after contracting the indices. Maybe this is not entirely clear. We do it very quickly in a corner, right? So we should do PA mu, eta mu rho, eta mu sigma minus 1/2, eta mu eta rho sigma. P, we call them M and M, rho, and sigma, right? That's why you always get this factor here. And then our beloved delta function. Now, as you can see, basically the only difference is that now we don't have a epsilon. Times the amplitude without any softening. There we go. Was a bit long. Okay, now the integral that we are facing now, if we want to integrate over, yeah. Ah, thanks. Yeah, sorry, apologies. Yes, thanks. Exactly. So now we want to define an integrated rate. So this will be the fully differential rate over phase space, right? We want to integrate, in particular, up to some frequency. So calculate the total number, I mean the rate for the emission of n soft particles up to a frequency omega. So this would be the integral, sorry, some theta function, omega minus the sum over all the frequencies of the soft particles times this d gamma, where maybe I should make explicit the dependence on the frequencies. Right. And the integrals are over the omega 1s and omega 2s, so all the differentials are inside here, right? Then, okay, we can be convenient to use the following trick. The theta function can be written as the integral with derivative, which is the delta function. And now, okay, it's convenient to rescale all the frequencies omega r by omega prime in order to isolate the integral over omega prime, right? Sorry, maybe I should have defined also together with this f. Okay, I should have defined also big F, which is the real part of small f. Because now what happens in this step is that, okay, you integrate over the frequencies that we will do momentarily, but all the other integrals on the angles are exactly the same as the ones that we had earlier. As I said, the only difference is that we don't have the I epsilon, so what we get for the integrals over the angular part of these measures is this, but with the real part. So the only thing that we are left with is this guy here. So for the same reason, let me also define some W, which is not calligraphic, which is just basically the real part that one up to some factors. Let me not bore you too much with the details. Is 4 capital F divided by mm. And then the last step, so we can look at the answer. Okay, as I said, all the integrals of the angles simply give this W, which appears n times in the product, and then they divided by n factorial here. So the integral I was mentioning is the following. So for each of these integrals over omega, then we will be left with something like we rescale, as I mentioned, all of these omegas by omega prime. This means that from each of these will come out something of the order 1 over omega to the 1 minus plus 2 epsilon, right? Exactly the same as this. And then this reduces to a beta function, right? So I have n factors of this form divided by their sum, right? This would be the n-dimensional, I mean, the n-variable generalization of gamma alpha gamma beta divided by gamma alpha beta times the. Now, here comes the sort of the crucial bit that I wanted to highlight instead of just writing out the final result, which is that the last integration is crucial because, as you can see, it gives you an additional 1 over minus 2 epsilon n, which essentially cancels this singular contribution. So finally, so each of these gamma functions goes like minus 1 over 2 epsilon, minus 1 over epsilon. Here they are, and the last one is cancelled by this integral. So approximated for a small. Very good. So again, this was just to show some intermediate steps, but the punchline is if you integrate over the phase space of the soft emissions, the final result for the rate exponentiates. It's an exponential of what? Well, of this combination here that appears raised to the power n. So now finally, comparing essentially the two blackboards, which I might do here. Let's see if I can fit this here. So the gamma of omega now summing over all over the number of emissions, gamma of n, which we calculated, is the exponential to epsilon, and also omega to the minus 2 epsilon, if you will, times the amplitude without soft emission. But now we also know that the amplitude without soft emission is itself infrared divergent, right? Not only this integral over the everything here to the exponent, this guy is also infrared divergent, and the infrared divergence is determined by this calligraphic W. The only thing is that we are doing now the absolute value squared, so you get e to the twice the real part of W. And well, as you can check that thanks to the fact that this expression for this W, calligraphic W and non-calligraphic W are almost the same, except crucial factors that I hopefully got right in copying from my notes. You get that this is actually finite, and it depends on the A0, the finite remainder of the exponentiation of infrared divergence, which does not contain any infrared divergence. Of course, the price to pay is that we have the dependence on the integrate, on the frequency that is decided to integrate up until in this phase space integral, and the dependence on this cutoff that we put, which Weinberg associated essentially to the resolution of the detector, but well, let's say that this is the starting point of the whole U1 problem in QED. Essentially, there have been mathematical papers on trying to make this more precise, but the bottom line to be taken from this is that when one integrates and calculates an inclusive quantity, so one integrates all soft emissions up to some resolution, then the infrared divergences that separately show up in the amplitude, so let's say in the elastic amplitude, in the alpha to beta amplitude, and the infrared divergences that show up in the phase space integral over the graviton phase space, they cancel out against each other. So this is because I do this sort of detour into IR divergences, but let's say it's a bit outside the main topic that was nicely summarized in the title, BMS and all that. Although there have been also connections, as we will see hopefully soon, the formula for the soft factor is very closely related to the formula for the memory, which is closely related to BMS over translation, and therefore there have also been ideas on how to dress asymptotic states guided by BMS symmetry to also deal with these infrared divergences from the outset, although I will not talk about it today. So, okay, let's start using this idea. And let's go back to our main objective, which is to arrive at the memory. So what I've said so far essentially is some standard quantum field theory material. Instead, our goal today is to eventually make contact with classical gravity, right? So now I will start discussing what happens when I take the classical limit. And well, the first step that I find convenient, although not entirely necessary to be fair, in order to get to the final result, is to rewrite the exponentiation of soft emission. So I go back again to the first topic we talked about today by introducing an operator, essentially, which takes the following form. The star will denote the same cutoff omega star that we had earlier. Will be a bit more precise, but on a different shortly. So the integral of free space. Let me introduce shorthand, otherwise I will spend all my time writing this. Maybe it's not the most useful way. And now the theta omega star minus k0. And then this W A dagger is a shorthand for sum of physical polarizations. Epsilon I mu k A dagger I k. And A dagger obey the canonical commutation relation. So they are annihilation and creation operators for gravity. Very good. So what I wanted to start from in order to approach this issue of the classical limit is to recast soft theorem in this way. The emission of n of these soft gravitons equivalently can be written by some I1 1 by n insertion of this operator, which, well, I will call like soft diagonal operator, but could be also equally well called displacement operator, I guess, according to slightly different notations and conventions in the literature. So the idea is that by the usual Baker-Campbell-Hausdorff formula, each of these a's pulls down the coefficient of a dagger in the exponent. So indeed, it will pull down the exponent soft factor by construction, and then the normalization is taken care of by just dividing by the leftover expectation of the operator. Right? So this is just a trivial rewriting.
Sorry, your zero here is it's got the normal and any particles over it.
Yeah, in a sense, exactly. It could be the background process. It's just a state with no gravity. Very good. So then a step which is convenient and which, well, again, for today's purposes, again, not really necessary, but in order to maybe introduce on the side some fact which can be used also in other contexts. When we consider this classical limit, in particular for a 2-to-2 process, it's convenient to introduce a Fourier transform of an amplitude in Q space. So here everything has been written down, as I said, in the standard PFT language, so amplitudes labeled by momenta, polarizations, etc. Well, in particular for the 2-to-2 amplitude, which is a function of the momentum transfer Q, let's say Q1, Q minus Q1 minus Q minus P2, it's convenient to introduce a Fourier transform which can be written down covariant in this form. 2 pi delta of P1 dot Q, 2 pi delta of P2 dot Q. So it's a two-dimensional, a D-minus two-dimensional Fourier transform in the space orthogonal to the incoming particles, e to the I b dot Q times the, let's say this is a function of B, of course, where B is the position of space analog of the momentum transfer, which is the impact parameter. Now, there are slightly different incarnations of this idea in the literature, but the bottom line is that when you take this amplitude here, let me call it A4, you do this Fourier transform, which I can note by a tilde, 1 plus I A tilde. So the amplitude, the 2-to-2 amplitude written in terms of the impact parameter takes a very nice exponentiated form, precisely in the classical limit, which for a 2-to process essentially means Vm squared over h bar very big, or if you want, h bar going to 0 naively, and is dominated by the exponential of a very large phase, which is usually called delta or I. So motivated by again the main this is a sort of a mini crash course on the Econon exponentiation. This is often called the Econon. I just want to say the idea is that it is more natural, it can be useful in order to discuss the classical limit to go to impact parameter space. One can also see it from different approaches, in particular from KMOC, by considering some wave packets. But let me take this as a guiding principle to justify that, well, I want to take the Fourier transform of this concept. So going to B space, what happens? Well, I get that there is a natural definition of a soft radiation, let's say, operator, which is the following. Our beloved delta SR, which inserts the soft gravitons times this phase here, which, okay, I can be more precise in the sense when you take the Fourier transform of this guy, you can formally pull out everything that does not depend on Q, but in a smooth way, right? By using the identity that, you know, Q mu is just the derivative with respect to B up to some factor of I, and then formally you can rewrite this as this operator times the amplitude, but the amplitude is given by this formula, in particular if I focus on the 2 to 2 case, but I mean, the result is more general. And so you would get something like this, in which the, I know it's a bit of a, I mean, it's a lot to take in just in a few seconds, but you remember in this delta star there are these W's. These W's are the functions defined by Weinberg that depend on the momenta, P1, P2, P3, P4, right? So the idea is that these are the P1, P2, P3, P4. They depend on Q, which should be integrated, but you can always rewrite this Q as derivatives, as I was saying. So formally, this is an operator acting on this guy, but, well, in the classical limit, this implies that, I mean, that the classical momentum transfer is precisely the derivative of the icona. So the only effect of doing this is to rewrite all the small q's or the momentum transfers in the amplitude in momentum space in terms of classical momentum transfer. So I know this is very schematic, but essentially this is a proposal for the operator that determines the final state for a classical process, and here the rest is just you take the Weinberg factor and you replace all the momenta with the classical momenta of the particles before and after the scattering. As I mentioned, this justification is not really needed for the final goal of today, but I thought it was nice to present some connection between this, let's say, completely quantum discussion that we did so far and this more classical setup. The only difference is that, well, thanks to the fact that we saw that the cancellation, that there occurs a cancellation, right, between classical soft emissions when you integrate over phase space and IR divergences, is that, okay, there is an additional subset. This delta would actually have an imaginary part, which is infrared divergence, but this infrared divergence cancels precisely as we showed, so the right thing to put here is real. So I know this was a bit schematic, but hopefully the main idea is clear.
The first line you already then took the classical limit for the writing that operator.
Here?
You already took the classical limit.
Yeah, here, I mean, this is just the definition, essentially, right? In a sense, the classical limit occurs here. When I go to B space, this identification that allows me to substitute the, you don't have the expression anywhere, no. This W contains this Q, right? Because it depends on the moment of the hard particles. And in principle, okay, that's it. This identification that I was mentioning, so that you identify Q with the derivative with respect to B by the identity of the Fourier transform. And therefore, with this classical momentum transfer, that only happens in the classical limit. I mean, I can be more precise, but essentially the idea is that in principle, you have derivative acting everywhere, right? You take the derivative of the phase, and then you can have the derivative of whatever you brought down from the exponent, or also again of the exponent. So then you have many terms, like in the WKB approximation. You say each bar is small, and then in principle you can take many derivatives of the exponent that you make an answer for. But then in the classical limit, the dominant contributions come when you always take the derivative of the exponent, because that's the thing that is large and goes like 1 over h bar. So yeah, the classical limit enters here. Very good. Now, I apologize if this connection was a bit shaky, but now that we have this ingredient, we are back on track, let's say. It will be more or less algorithmic from here on. Yeah?
In the classical region, the S matrix acts by this phase and also by the soft radiation.
Exactly. So, I mean, this goes back to, of course, the proposal in a paper by you and Andrea and other collaborators. So the idea is that the final state of a classical collision is the first approximation where there is a deflection, which is encoded in this phase, and then there is a coherent emission of gravitons. Okay, in this case, it's not really a proposal, it's a theorem that has been already proven by Weinberg because, well, exponentiations for the soft part of the spectrum do exponentiate.
The soft limit.
Exactly.
And everything is
exactly. Very good. Now that we have this, we can use the strategy in our very, very widely employed in literature, and that was first pointed out in a paper by Donald and David and Ben maybe. Let me first read. So and then elaborated upon in the context of waveform calculations precisely, which is a topic of our interest today. in this other paper here, also with Andrea Cristofoli and Riccardo Gonzo, if I'm not mistaken. So the idea is that if you want to calculate a classical observable and have, well, either you know the S matrix or you know this sort of simplified version of the S matrix that we have cooked up, well, you can just take the expectation value of that operator you're interested in the final state predicted by the S matrix and get in the classical limit a reliable expression for your observable. And so the idea for the rest of the lecture is to apply this formula for some observables of interest. The first one is going to be the metric fluctuation, essentially, or if you want, the canonically quantized metric fluctuation projected on physical polarization. So this guy here. This is supposed to be an A. This is supposed to be an A. The matrix. So this is what we want to insert. Now, again, what comes to, okay, to be precise about normalization, let me recall that this is the canonically quantized and therefore canonically normalized metric fluctuation, whereas it is a bit more interesting to calculate the, well, the dimensionless metric fluctuation, right? So this is eta mu nu is -1 plus 1 plus 1 plus 1, so this is dimensionless. Instead, this guy has dimension of an energy, and the right normalization factor is this one, square root of the equation. And okay, so our job is to substitute this operator into this expression and then use the formula for, let's say, the soft Ekman operator. And once again, now let me do this step a bit more in detail since it's somehow more relevant for us now. Each of these, I mean, it's enough to calculate the expectation of this, right? Because then this other piece will be obtained by complex conjugation. So we have to use the AI in the final state. Yes, if I don't write any state, it means that this expectation in the final state. Well, there will be e to the minus 2i, okay, real part of delta, but to our order is not important. And then e. Spin, and then AI. E to the plus. And here, of course, imaginary part, sorry, e to the I real part of the delta will cancel out, but I wanted to put it again to remind again this mechanism I was trying to sort of sketch, which is that, of course, it cancels, but it is important because its derivative provided the interpretation of the Q's appearing inside the W, right? So, okay. Now that we learned that, we can raise it. And then we can use the usual formula for sort of Baker-Campbell for one corollaries I never remember, which means that this sort of exponential sandwich can be written as the exponential of the commutator, right? So this is going to be this.
Why do you use the two S matrix in that?
Yeah, it's a bit hidden. It's here, right? So the 2 to 2 exponentiates when we go to impact parameter space.
That S is an operator, so you could insert a arbitrary state.
That's true. That's true. In fact, I mean, essentially, it's a bit beyond what one usually discusses in the iconal of the 2 to 2. The idea is that to leading order, at least delta 0 will probably exponentiate even in the classical limit of n to m scatterings of massive particles, as long as all the impact parameters are sufficiently big and all the masses are sufficiently large.
So 0 here means
it's
just
just
gravitational state,
exactly.
but maybe like,
Exactly, it could be in the background of a generic process. Yeah.
You're talking about, I don't know, merging, be the final state,
Yes, yes.
the single object after the merge.
Yes, I think so, yeah. It's a bit tricky when you don't really have any asymptotic states in final pass, but in principle, you can think that your asymptotic state in the past is a merger of two objects, and in the final future, you have just a final bound state. A bit tricky to set up in QFT, but in principle, you can think of that. So this would be the exponential of the commutator, right, of this thing. And then I never know how to write this. Let me put a dot. But of course, the exponential truncates, right? Because the first one is just the identity, which gives 0 because A acting on 0 is 0, and so the non-trivial, the only non-trivial thing is the commutator between A dagger and A, which is the again, which is the delta function, right? So this brings down value I. Okay. Or more precise, yes, just a second. Please.
So in the expression for S, there is an implicit dependence on the impact parameter.
That one?
That one. Is there a dependence on the impact parameter?
Yeah, I apologize. It was a bit quick. It's inside this phase, right? Okay. So just to be concrete, the hidden order iconal phase would be something like 4G and 1 and 2. I think sigma square minus 1/2 divided by B equal to sigma square minus 1, something like this. Well, the cube, so the derivative will be. So sigma is, is what I was calling sigma 1, 2. So if you want, is the relative, it's connected to the relative velocity in this way. And so the derivative of delta 0 gives you this. Depends on B.
So the expression for the observer is really a 2 to 2.
Yes, so for simplicity, I'm just writing it down with the iconal phase, but then as Bart was pointing out, this idea is more general. You can think that, okay, maybe here it's not just the usual iconal we all know and love, but I mean, the classical particles will reflect in some classical way, even if it's 3 or 4 of them, right? So it's more general than that. You can really sort of promote it to be an end-to-end process, and in fact, in the final formula that we write, it will be clear that the only important thing is the expression for the Weinberg factor, which is summed over n particles. So everything we will derive at the end is actually valid for a generic end-to-end process, and for generic states, masses and the momenta are important, but the spins and the tidal effects are irrelevant. So hopefully that should be, if not clear, at least convincing enough from the final formula at the very end.
So you see that if I have 6-point field level amplitude, then this formula on the right.
Yeah, no. I mean, I admit that this is beyond what I'm technically discussing on the blackboard, right? So it's I agree. This is just for 2 to 2, but I'm just advocating that as physicists we expect that even 3 to 3 or whatever particles will have a classical limit, right? That's all I'm saying. I don't have the expressions for loop iconal phases for 3 to 3. Yeah. So very good. This brings down this factor here. So our job now is to just perform this integral here when A is substituted with the W.
2 to 3, but let's say some inelastic process like 2 to 3, the classical would be perhaps suppressed, but
Exactly.
suppose you're scattering charge object that you can emit photons, which are, that would be also classically allowed.
I guess so. Yeah. As long as you're sorry.
You would need to include some inelasticity.
Yes, exactly. All these details are not on the blackboard. I agree. It's just the physical expectation. I'm sort of trying to advocate, right? No, the kosher, let's say, thing I'm writing on the blackboard is just 2 to 2 dressed with some subgraviton, which is arguably more interesting because 2 to 2 processes are they're still unlikely, but a bit less unlikely than 3 to 3, right? Or 2 to 3 with some care.
Classical, let's say, Gedankenexperiment.
Yeah.
Classical charge black hole.
Yes, absolutely. So there would be a
photon
that itself would emit a soft gravity. Yeah, that's also. I think the final result will also hold for that process. So let's erase this. So we have to perform this integral we just erased. Let me write it down again. This is our metric fraction, and this is just the integral over the phase space factorization. And this brought down the epsilon star, right? So star from sigma W rho sigma e to the I k dot x plus convex one. So okay, this sum over polarization just produces this TT projection, right? This is well, easily can be written as pi mu rho minus sigma minus sigma pi mu rho minus pi mu pi rho sigma, and this pi mu is the transverse projection. With lambda reference factor satisfying this property. So okay, this is there just to remind us that we have to put the physical polarization, so for instance the TT projection at the very end. So basically our job now is to calculate this integral here. And okay, actually whatever prediction we get from all this machinery, it will only be reliable out, I mean, far away from this process. Of course, it will not hold in the proximity of either object or for instance, one of the two black holes or n black holes as we were discussing. So we actually want to calculate this limit as r goes to infinity, u fixed, and n goes fixed. Let's say more precisely, we want to evaluate it at a point x mu, which is u times some time vector plus r and mu. And here we essentially make contact with something that we discussed last time. So u is really the retarded time of a detector, r is this luminosity distance we produce, and mu is null vector that satisfies t dot n is equal to -1. So if you write it down in components, it would start like 1 and then a unit vector, right, in the frame which is at rest with this for velocity t mu. So the question is, how do we take this this asymptotic limit? So we are now trying to evaluate this limit at prime. We have this drawing, radiation is flowing away from this n to m or 2 to 2 process, and we want to see what happens here, right? So, well, I thought I should present this in maybe a bit more detail than some other steps. So let me try to do that. I mean, there are several ways of taking this limit. One is to reduce it to the sum and difference of advanced retarded propagators. But maybe I can sketch slightly different derivation. So let me simplify the problem a bit. Instead of writing really down all the indices all the time, let me consider this function here. So essentially suppressing all the indices, formally writing this as a Fourier transform with some phi tilde. And then our job is to take that limit over here. So it's convenient to introduce some integration variables that sort of match this definition of the retarded variables. So k mu equal to rho t mu plus omega m mu, where with t velocity squared equal to -1, right? This is really the forward velocity of the detector, if you want, right? So satisfying again t dot m equal to -1 and m squared equal to 0. So then we have to do we have to work out the change of coordinates or variables more precisely. Well, let me write this as dm, although this could be more precisely written as dm dxa, right? You remember these angular variables that we had last time. So this is a two-dimensional element, of course, because it satisfies these two constraints. And then the metric is just -0 squared -2 d rho d omega. And then most cross product gives 0, right? Because t times m is minus 1 gives this thing, t times dm is 0 because of this constraint, n times dm is 0 again because of this constraint, and okay, the only one that remains is omega squared dm squared.
So you've just introduced the basis, T.
Exactly.
And, I guess.
Exactly. So I'm using as basis vector, let's say t mu, and then essentially the rest is parameterized by this null vector, which is effectively two-dimensional, right? Because of it's on the light code.
You're not lining them up with any polarization vectors. It's just completely.
No, for the moment it's just an exercise. Suppose we forget everything about the physics. Suppose I given this integral, I want to calculate the asymptotic limit. What happens? Exactly. So then, okay, as you can see, the Jacobian is very simple because the matrix determinant is just omega to the d minus 2. The square root of the determinant. And then we only have to work out what sits inside this measure here. Maybe let me write it down once. Delta k 0, delta k squared, right? So then we substitute this form and we use the definitions. And if we don't make any mistake, this is just theta of omega divided by 2 omega. So this comes from taking the derivative of the square. Usually the usual identity that delta of f is delta of the solutions f equal to 0 divided by the derivative in delta of f. So not surprisingly, this sets to 0 this component here. So it means that k must be null. Thanks a lot. And okay, inserting everything, you get integral from 0 to infinity. The omega over 2 omega. Integral over this d minus 2 sphere. So sorry, apologies, I keep changing notation for this measure on the sphere, but this is what I was sometimes calling d mu. I mean, it's the usual measuring on the sphere. It's just that it's a bit awkward every time. Introduce slightly different notations for that. Omega d minus 2 by tilde omega n, right? Because the t mu component has been set to 0 by the theta function. And then the exponent, we can expand it a bit in e to the minus I omega r plus I omega r n dot m. Up to here is just a rewriting. I didn't do anything actually. Now we want to take into account this r tend to infinity limit. So as you can see, here comes, let's say, the part that is a bit less algorithmic. Well, if r tends to infinity, the way to compensate for this is by looking at n very close to n, right? Because n and m are non-vectors. If they coincide, this thing can compensate the fact that r is going to infinity. So let me now further change variables by introducing n equal to n plus some z. And of course, since both n and m are null, 0 must be equal to 0 plus 2n dot z plus z squared. So essentially what I'm trying to say is that z should be small, and of what order? Well, of order 1 over square root of r, right? In order to compensate this growth, because I can use this identity here and rewrite this as follows. So since z is small, I can pretend that m is equal to n everywhere else. So this is effectively I'm going in a collinear limit, right? Maybe to emphasize this, let me pull out by tilde of omega n now. Integral dt minus 2 z divided by 2 pi d minus 1 omega, well, the omega I could have pulled out as well, e to the minus I omega, sorry, this is omega u, of course, because from the product between here and there. And finally, 1 over 2, yes, z squared. Now, again, this omega I could have pulled out. Now, the benefit of doing all this is that this integral is Gaussian, so we can do it. And the result is the following. I 0 to infinity omega to the minus 4 over 2, because 1 additional powers come down from there, and phi theta. So this is a relatively general formula for the asymptotic limit of integrals of this type, which reduces them to integrals over omega, as you can see. So now what I want to do is to apply the result of this exercise to our original problem, right, in which phi theta is the TT projection of our W plus the complex conjugate there. So then, let me try to do it here. I will get, well, everything then we will do in d equal 4. So as you can see, this simplifies matter quite a bit, by the way. Yes, 1 over 4 pi r, where you can recognize this thing that also could have come by rewriting this as the, essentially the retarded propagator evaluated asymptotically, which is also another possible way of doing this calculation. 2I pi W transverse traces, and at the end of this notation, right, instead of writing the contraction with the projector over there, omega n, where now I emphasize that n is the observation direction, right? The integral has localized the angular integrals to be along the direction of observation, plus complex conjugate. Now, finally, you can check that the explicit expression of W actually satisfies that Wk star is actually minus W of omega of minus K. And using this property, you can erase the CC and put the minus infinity here. So you can, the two integrals reconstruct the integral over negative and positive frequency, roughly speaking. You see that it's crucial that we have this minus here because we have an I here. And so two things combine nicely. So this is the final result, essentially. By the way, this is, I performed this derivation for the soft case, but essentially a very similar derivation works also beyond the soft case, but to leading order in the small deflection approximation or the post-Minkowskian approximation. Very good. So we're almost there. Just need to do the final integral over omega, since now I get the explicit expression for W. So let me.
The integrals you just did are, yeah, so, all right, maybe I didn't quite understand. Usually people say, I'm sorry, that this is exact in the leading order in 1 over distance.
Yes, exactly. So this is the leading order for large R. Then there would be corrections if you want to go subleading in R, right? So this, sorry, maybe here I could have put a squiggly line.
You're saying that in the derivation you did here was specifically for soft, for small omega?
No, vice versa. I tried to say the opposite. That this derivation is completely generic, does not rely on the.
But in this soft case, it happens to come out as 1 over R.
No, okay. The 1 over R, as you can see, is really just a feature of how, of the fact that you are on shell in a sense, right? That this is just the integral over delta omega squared. So this is true for, let's say, roughly generic solutions of the wave equation. Now, what I wanted to say is that this whole derivation in which you insert in the final state, sandwich, the operator, etc., we did it by calling this thing W mu nu, but it works, as you know very well, in the same way, even if you just insert the waveform to leading order in the PM approximation. It does not depend on a specific expression that our. Sorry. So plot number 3 is here. Very well. So now instead we use the explicit form of our W, which goes like 1 over omega, and hopefully get to the one of the main punchlines of today. So essentially, as you can see, we are faced with remember this guy goes like 1 over omega. More precisely, it's the sum of n ingredient each that is of the following form. This I just copy from there. And then 1 over dA k minus IT. So now what we can do is, remember I introduced this eta at some point, so PA mu is eta A Ka, where Ka is the true momentum in a sense of particle A, so with the right sign and with the right sign of the time component in particular. So we can factorize this. I mean, we can pull out Ka times, you remember, okay, so let me write it down again. K is localized as omega times n mu. So this becomes minus Ka times n, the integral omega u divided by minus, here I pay the price of my immoral choice of choosing the mostly plus, which I have to put minus signs everywhere. For that. And now, okay, it's convenient to change the integration variable to be omega going to minus e omega. Notice that this does not change our integration domain, which has been extended to the whole real line. Minus k, and they just copy and then just put it in the final form if they want it. E to the plus I omega u eta a divided by omega minus a. Very good. And this integral is we recognize as one of the representations of the theta function, right? When this object here is positive, we can close the contour in the upper half plane, and therefore we pick the residue at plus I0, which is here. Instead, when this guy is negative, we can close the contour in the lower half plane where there are no poles. So this is exactly, and the 2 pi cancels the line from the residue formula. So the result, maybe I write it here, is of u eta. Very good. So now we can simply substitute this. This will be summed, right, in the expression for W, and then transverse tracers projection, and the final result is the following. Or, well, asymptotically leading order in R, U and N fixed for T over R, over A, running over all the states, which are 4 in the case of 2 to 2, but as I try to advocate, pretty more general than that. And the divided and equal u eta. Very good. So in fact, I forgot to write down the reference, but well, this was essentially given first in a paper by Andrew Stromener and Sasha Riboidov in 2014, and shows that the Fourier transform of the top theorem is the memory effect in the following sense: that, as you can see from this theta, I mean, I can write this down in a bit more perhaps transparent way by splitting this in the sum over the in particle. The theta of minus u, right? Because eta A is minus 1 for our incoming, and the sum of the out. Theta of plus u. So if one plots, let's say, one of the two polarizations of these at fixed angles as a function of u, let's say W, or I'll go to call it H, maybe. As a function of u, cross to the plus, it will do something like this. Oh, by the way, nobody complained, so I didn't say. At some point, as you might have noticed, I dropped the cutoff of omega star, right? It should have been in the measure I was writing at some point. But the idea is that as long as we consider u sufficiently big, the cutoff is not needed. In fact, as you can see, the result has not been divergent. But the price to pay is, of course, whatever we got is only valid for large u. So there will be some region in which I cannot really predict much using this approach. So in other words, small omega translates to large u. larger at the time, whether positive or negative, but we can predict the asymptotic value, asymptotic constant value. Here it's going to be given roughly by sum over house, let me say, and here by sum over E. And the difference between the two is the so-called memory effect. So the fact that the gravitational field does not go back to its initial value after the passage of the gravitational wave, but rather it experiences a sort of jump. And as you can see from this formula, the jump is precisely the difference between the final momentum in these expressions, evaluated on the final momentum and the initial momentum. So sanity check, if the particles did not deflect and didn't do anything, the memory is 0. If instead they deflect, the difference will be essentially proportional, or depending on this deflection. For instance, to leading order in the small deflection approximation, you can check that this becomes again proportional to G, so this is of order G squared. In the whole expression I wrote. Well, the memory that you get by taking the difference between these two times the G is of order. Okay, so this is the first. Maybe I should pause and ask if there are further questions on this. Maybe in the meantime, I can start raising the other one. Well, this derivation sort of brought us back to null infinity in a sense. And what I want to do next is to show this intriguing connection that that relate this memory effect to the super translations, and then if it then sometime remains, we might. Yeah.
I mean, you got the expression in the TT gauge because you picked a particular physical projector.
Yeah.
Of course, you could have got it in various other gauges.
Yeah.
Is that going to be relevant for the BMS transform? I guess you're going to do BMS.
Not really, not really. In the sense that eventually, what we will see is that when we go to our Bondi setup, really only the TT part of this will be relevant, in the sense that we will project to this celestial sphere that is AB, capital AB component, and essentially only these the components orthogonal to the asymptotic light front will be relevant. But it is true that it is not really something that has been very much discussed in this connection. So my interpretation is the following. Maybe you can say if you agree after I go through. But another comment that I might add is that if you were instead to look, for instance, at the psi 0 or the Riemann tensor, then there's some additional derivatives, right, with respect to u. So if you plot it, you would see something that does not show manifestly the memory effect, in the sense that it would fall off at infinity, right? Both at u goes to plus infinity and as u goes to minus infinity. So then you would have to integrate to go back. Maybe it's a bit less transparent, the description of the memory in terms of that, although, the gauge invariant information should be there as well.
About that, I mean, this is just a linearized Schwarzschild. All you've got here is difference between linear and Schwarzschild.
In a sense, yes. Although in a sense, linearized Schwarzschild, the TT would kill it, right? Because essentially you would need to have the radial derivative.
But boosted Schwarzschild can't be anything else.
Yes. In a sense, yes. It's even a bit less than that, I would say, in the sense that
it's some components of it.
Exactly. You, for instance, suppose you were to calculate the charge using the formula that I gave in the last lecture, you would find 0. But that's just because you put this stupid, let's say, TT projection. If you just remove it, then you get also the charge. That the initial mass is the sum of the masses, also the energy of the particles and the momenta. But no, I agree. Yes. So this is a glorified way of getting the sum of n to m boosted Schwarzschild. In fact, there is a nice paper by Bob Wald and collaborators, Tolish and others, in which they do precisely that. They solve the wave equation for a static particle created in the origin, which is essentially what brings about these theta functions. Then they boost them, or they consider charged particles first as a warm up, and build this exactly from boosting static solutions.
Yeah, I guess what I'm saying is if you have the curvature, it would just be the same. Of course you've got more derivatives, but it's just because it's...
No, the information should be the same. I agree. Yeah. Very good. So exactly. Now let me make contact with this super translation I was mentioning. So let me start with an exercise, which is, now remember I was introducing this XA coordinate with our angle. So if you want these parameterized, the n, the d minus 2 coordinates on this section, right, the satisfied t is equal to -1, or if you want 1, comma n in the notation that we had last time. And then let me recall also this nice property that the n satisfied. Well, I can write it. Where gamma AV is really the metric in the sphere, so let's say a n dot n. The nice identity will be useful in the following. So the exercise is to calculate the knowing the result. Where v is just some vector with, I mean, it's basically it will be the velocity of our particles, some vector with whose magnitude is a bit smaller than 1. So, in order to calculate this, let me first focus on the action of this operator. And by the way, these are the covariant derivatives with respect to this metric gamma, and the Laplacian is the contraction of this covariant derivatives on the sphere. So let me focus on the action of this, because then this guy I can always obtain by just taking the trace, right? So let me consider the ADB for the moment. One derivative. So we get the derivative of this. And then the log speed plus, well, if I can log the 1 over the argument, will kill this piece over here, and then minus dB and dot v. And then I the other derivative. So when I act twice on this guy, I will use this identity to bring gamma beta and dot v log. Then I have to act on the log, which brings plus. Sorry, I put it. dvn dot v, because I took the derivative of what was inside the log, and then I have to divide the argument. And then, in principle, we go to this guy over here, here plus gamma v and dot v. Very good. So now, as you can see, when I reinstate this term with the gamma, I mean, essentially what I'm doing is I'm subtracting the traces, right? So these two pieces will go away because they are pure trace. And the result is just going to be a traceless projection of this, which is, let me write it down. Minus 1/2 gamma AB, and then I will need to contract this with gamma AB upstairs, I mean upper superscript indices. But of course, this is just the magnitude of the projection of the vector n orthogonal to the sphere, right? So by Pythagoras theorem, this is so the hypotenuse minus the square of the other. How do you say cateto? Well, you know, this high school math you learn in your mother tongue, and then okay. So this is the result of our exercise. On the other hand, we can also calculate now this TT projection explicitly, right? So what does it do? Well, well, to be precise, I have to choose this vector, right? I was writing down in my TT, my TT projector. Remember, this was what was involved in the TT projection, but we can choose this in the standard way, right? It would be 1 over 2 omega 1 minus n. Is that the way that we satisfy this? Sorry. Lot of k over 1. And you can check that this is nothing but, okay, let me do it for the 0, 0 components, would be minus 1 plus 1 half plus 1 half, so this is 0. Same happens for the off-diagonal components, and here you just get the projection on the sphere. You know, the projection orthogonal to the sphere, namely on the tangent space to the sphere. And therefore, maybe I can fit this here. And therefore, the contraction between the EA, EB. So maybe I should introduce that earlier. I mean, these vectors are just the basis vectors on the sphere, right? And I could have equally written EA dot B, AB dot B. The TT projection of, say, B. What is it? Well, it just, we have to do this. Only this piece over here matters thanks to the 0. And so we get EI B. Pi I K J L minus 1 half pi I J K L B K B L. And this is precisely what we have here essentially. So as you can see here, the E are already orthogonal to the sphere, so only the delta part, these ones matter, right? So this is effectively contraction with delta ij. So this is EI is precisely what we are expecting here, and then minus 1 half. Here instead, only for this guy, this contraction is important and gives gamma, right? The contraction of EI EJ is precisely gamma. Gamma AB. And then here we get precisely this contraction. So delta gives the product of these two guys. Unfortunately, I arrived at the very end of the blackboard. Apologies for that. I don't know if it's visible. It's exactly the combination we have here in the numerator. Okay, so what we have shown is that this combination here, of course, you can multiply both sides by this denominator, which is inert under TT projection. We have shown that the action of this operator on this specific function here produces exactly the function that we have in each term of the memory, right? So I will now way arrive at the second sort of punchline or take home message of today. Which is that the TT projection of this, maybe I should call them A in analogy with place to the invariance. Given by, okay, there's an M. Now if we want to restore the proper dependence on all the dimensions. Where VA now is the velocity really, so KA divided by MA, the velocity of the eighth part. And now I I had written at some point on Blackboard the last time that the action of super translation is precisely involving this operator here, right? I was writing that the real derivative with respect to super translation vector T du minus 1 dp dA plus half the fraction of T dr plus the leading order is precisely R times T du minus. There we go. So in our case, our C would be the projection of the memory along this this component. But as we so this du, you remember, would let me separate it quickly. Roughly speaking, the signal that we could predict using the soft theorem was just a constant for negative u, and then something in between which you don't have access to, and then the final value. The initial value being the sum over the in, and the final value being the sum over the out, but reduced into a constant. So in our case, this derivative with respect to u would kill this constant part and would give something localized in the bulk, let's say, of the interaction, which we don't have access to in our case, and in any case it falls off very fast at infinity. So what remains is this piece here. So in other words, what we have shown is that I really should not have erased that formula. Is that the well, the memory can be written. I mean, the form of the wave, I mean, the waveform itself. Let me write it down in order to have some final point in the Blackboard. And then everything is, in a sense, pure super translation. So everything can be written in this. Sum out minus n dot va log minus n dot va, and then let me not write everything very explicitly. Equal minus u times the same thing but with the sum of the in. Plus, in principle, I mean, we can do whatever we want with each of the factors. We can write some parameter xa, and then the same. Oh, maybe okay. This is actually a compact and precise way of writing. So you remember the formula we had earlier only had this piece here and this piece here, right? Theta of u, positive u, sum over out this thing. We simply rewrote it using the identity that we showed as an exercise, that each of the terms can be written as this operator acting on this log. Then we had the theta of minus u sum over in, and then if we believe Bondi, Metzner, and company, we are allowed to super translate the result in any way we want. So in particular, we can act with another super translation which adds this piece here. So for instance, if we really want to, we can choose that x is 0 for the out particles, and this is -1 for the in particles, in such a way as to kill this piece over here, and therefore move the drawings that I was making, that was sketching. So here with the sum over the in, sum over the out. We can choose this xy, this xa in order to go to this situation, right? So we have 0 in the far past and sum over out minus sum over in the final, in the future. This is our super translation freedom in a sense. But maybe what is even more interesting is that the memory itself. So when you take the difference between these two, this piece goes away, and you again find this sort of super translation invariant expression itself for the memory, because you take the difference between positively new and negative u, this piece is killed. But this difference is again itself pure super translation because we wrote everything in this form. So this is essentially closes finally the triangle in a sense. So let me maybe reiterate very quickly. We started, I mean, last time we discussed these asymptotic symmetries, which were obtained by studying the asymptotic properties of isolated or weak radiating systems. In particular, our exercise of studying the residual killing symmetries led us to identify, okay, translations, rotations, boosts, and then these additional transformations over here. Then today, we started from sort of an orthogonal line from the soft theorem, which in principle seems to have nothing to do with that, and we deduced from that the memory effect. So we essentially inserted the operator calculating the gravitational field in the final state of our, in the center of the final state obtained by acting with this soft iconal operator, or with essentially dictated by the soft theorem, and the final result was this memory formula. And then we have actually realized that all the terms in our memory formula are in a sense pure supertranslation, that they can be written in this way. And in particular, the difference between them is also supertranslation. So then if I were to complete this triangle, the missing link would be to show that the supertranslation actually allows one to prove, in a sense, the soft theorem. So there are charges associated, the ones that we wrote down last time, that can be used to sort of give a derivation of the soft theorem itself of the factorization by implementing them as word identities, in terms of word identities in the semi-classical theory. As I said, I wanted to, since it's more or less along the same lines, following the KMOC idea of inserting final operators in the final state, I wanted to still present a couple of other observables. So this would be really unobservable in the sense that the metric at the interferometer would not go back to the original one, but actually produce this constant shift. The other observables I want to talk about is related to the energy emission spectrum and the angular momentum. So, yeah.
Quick question. So at this level, not the gauge transformation, right? A linearized gauge transformation.
Yeah.
That's all it is.
In a sense, yes. In fact, as I also mentioned, I think last time, you can also derive this whole algebra just from the linearized setup. The only difference is you will not see this transformation here, but as you correctly point out, in this case, it's not the relevant one.
Higher orders, it isn't necessarily just a linearized gauge transformation.
No, exactly. In fact,
it happens to be.
Exactly. So this is really just the leading order. In fact, if you plug in let me make this comment, which is actually important, I was forgetting. So now suppose we consider this formula, we do not, for instance, insert this, so we can choose it arbitrarily, but go in the post-Minkowskian limit, right? So in this case, the final states, P3 and P4, are related to the initial one, right? In this way. And Q is small, of order G, roughly speaking, right? So G is the power coming parameter of this small deflection approximation in which the particles interact with. Now, what happens is that here, let's say we take for as a standpoint the fact that the incoming particles are fixed and the final state differ by the incoming ones by a small quantity. Then to leading order, we can just neglect. I mean, you can show that this reduces if you don't put this extra XA, choosing, shifting this, you will find, you will get a situation in which to order in the PM expansion, the waveform is just given by sum over 1 and 2, so incoming, PA mu, P3 divided by, I guess, minus PA. So there is a constant piece in the what do you say, waveform is a bit strange word because it's constant. So what is fluctuating? It's not a waveform, maybe a constant gravitational field. But this is pure supertranslation, so you can apply this shift, linearized gauge transformation, to kill it. Now, if you go subleading orders in the post-Minkowskian expansion, things complicate, and we have, in fact, Stefan wants to work on that in the room. And the idea is that, in particular, the first order which you see the action of this fit is precisely the sub-leading order. So when you have G cube overall. So at that order, precisely this piece starts being important. The non-pure gauge one, in a sense, if you allow this sort of mixed terminology.
It just seems funny then to say that you get charges from just something that's pure linearized gauge transformation of these low orders. I mean, it seems has more life beyond that, but
So I didn't catch the first part of the comment.
You've just got a linearized gauge transformation to lowest order. I mean, it seems bizarre to say I'm getting a charge out of that.
Yeah. In fact, yes. At the end of today, maybe I present something about the angular momentum, and already the error of angular momentum was already this piece seems to be important. But maybe that's a question whether that angular momentum is actually measurable. Say this really smells of pure gauge, being pure gauge, and therefore. But let's cross the bridge when we get there. So now that we have developed all this machinery, why limit ourselves to just the memory, right? We can do more than that. In particular, we can insert, for instance, we can insert in this final state the energy momentum of the gravitational field. So this would be integral k alpha a dagger I sound over I. And okay, the algebra is very similar, right? The A's pull down the A daggers, coefficients, etc., and eventually you get an expression of the following type, where here you can either insert the projection over physical polarizations or contract with this sort of the Donder-like. Okay, let me note by prime the trace. And then in principle, this would be the correct formula for the total emitted energy if I didn't put any cutoff, provided here I put the full waveform. Since today we are a bit less ambitious than that, I still put this cutoff, right? So what we get is a portion of the emitted energy momentum. Here we put the emitted energy. This will be something like this, hopefully decaying for large omega. And what we are calculating today is the portion that really comes from things smaller than omega star, which is to be concrete for a 2-to-2 process. It means that it's smaller than 1 over the impact parameter. Right? So omega star is smaller than 1. Very good. So actually, what we can calculate is, we can calculate this integral or almost equivalently, right? The derivative evaluated at as omega tends to 0. So this is what I'm going to call dA over the omega. Omega to 0. And well, all the integrals are essentially the same as we calculated earlier on. In fact, they are exactly the same as those we calculated for the infrared divergences, except for the fact that there is no integration over the frequency, right? You remember there were these angular integrals sitting, doing all this weird stuff with the arc Cauchy, and then there was this final integral from 0 to omega star, the omega divided by omega, etc. Now, the only difference with respect to those integrals is that we are multiplying by an omega here, right? This k0 is the frequency, so there is no 1 here, and we're also taking a derivative, so it is 1, right? Your plus over epsilon. So the result for the integral is exactly the same, and I already introduced, I think, the symbols earlier on, and the final result is the following. In fact, this is, remember earlier there was this -1 over 2 epsilon, so essentially -2 epsilon times this imaginary part, or the infrared divergence. The infrared divergence is the energy spectrum. I think there is a 2. Although there could be a 4 because I do not quote me on this. I think there is a 4. But the idea is that you can derive it straightforwardly from the infrared divergence. And then is our beloved -1/2. Okay, so here, I mean, this is one of the formulas that was sort of claiming that is suggestive enough to claim that the thing is completely general for end-to-end processes, right? Because here, I mean, this is as general as the soft theorem, clearly, just the sum of run and m, independent of the momentum, which I enter via these invariants, sigma and m, and their masses, and there's nothing more. So maybe before moving on to the angular momentum, aside from, we calculated the result we are having, a comment, which is the fact that this formula is actually rather useful if you want to study the limit of high energy for the 2-to-2 process. In particular, you can check that if you write down explicitly the sigma 1,2, okay, sigma 1,2 is just sigma, or Lorentz factors, and sigma 2,3 only, sigma 1,3 only differs by order q square contribution, but in particular sigma 1,4 and sigma 2,3, which are the ones essentially associated to the particles with the same mass, right? In my labeling, these are the same mass, and 1 and 2 have the following form. And as you can see, they appear in this arc cosh and also in this square root. Now, the reason I'm saying this is interesting is that Q, to leading order, Q is related to the deflection angle in this way, and if we stay in this small deflection approximation, this is just P times theta. Now, suppose we want to study the high energy limit. So P, okay, there is an identity that links P to the masses and to sigma. This is an exact thing. And then, so we want to approximate this for large sigma in the limit of large velocities close to the speed of light. So this become, up to factors square root of m1, m2, and sigma, right? Because the sigma here, this is one of the sigma here. And now, okay, this function here, you can study its analytic properties in a complex plane, and it turns out that it has a branch cut when this is equal to, its argument is equal to -1. So in particular, in the unphysical point in which q squared is equal to minus, so q is equal to minus m squared. So as you can see, theta is going to be, if we can keep it fixed, we can consider a large impact parameter and large velocity limit in such a way that theta stays small, but we have no control over this factor, right? So in particular, at some point, q will exceed this bound, will hit the branch point of this function, and therefore what we learn is that the small q approximation, or the series for small q, will start to diverge where sigma is of order 1 over theta squared. So this is a bound on the validity of the small deflection approximation.
Yes, bound.
Sorry? Yeah, the depth and the color centaur, and also probably there were previous works. So we decided with Paolo and Gabriele never to call it anybody's name. But yes, internally we used to call it color centaurs, but then there were works of depth before that, and then we were not exactly sure.
What's the first paper you?
I think it's the depth.
That's been around for a while, so
I think it's depth, about the first one that I know. Also, we had some other papers with pain, some sort of jokes about work. Very well. Now, since I'm almost out of time, let me just sort of deliver the punchline also for another observable, which is the angular momentum. You insert, instead of P, you insert this angular momentum in the gravitational field. You do all the integrals, which are almost the same as the one we did today, or we sketched today, and you find the following result. CNM G sigma squared minus 3 sigma squared minus 1. fine. This is the last time I write it down. Okay. So, and notice that now there is no derivative with respect to the cutoff or anything. This is really a finite contribution that comes from integrating from 0 to omega star, but does not depend on omega star. So the only possible conclusion is that it's something that depends on the. I mean, it's formally a delta function. I don't know how to, for small frequencies. I think I'm calling it. So this is sometimes referred to as a static contribution to the angular momentum loss, and okay, you can check that leading order it starts if you substitute these expressions for the invariant, it starts at order g squared, and in fact it's a nice expression if it's valid up to order g cube also. So small g up p1 minus p2 alpha 2. And there is a function which I will not write down because I'm out of time, but it's an explicit function of sigma that you can find, for instance, in the paper by the Moore 2020, and then last order g to the fourth. So the prediction for the coefficient in front of this delta function is actually known to order g, which is when you substitute here the order g deflection, the leading order one, and also g cube when you substitute here the subdivisions of q1pm and q2pm. So yeah, and to come back to the point raised by Donald earlier, somehow the issue is that if you were to perform this calculation, but either changing the epsilon prescription or doing this shift, right, I was saying, from a frame, let's say, in which the waveform goes back to 0 at minus infinity, to the frame in which it goes back to P1, P2, roughly speaking, you change this expression. So this is correct in the frame in which you really have the Coulombic field or the static field of the initial particle. If you go to the other one, this is 0.
Sorry, I mean if you go to a frame such that in the past the h is 0, then this is 0 too.
Exactly. And then if you maybe followed a bit this sort of series of papers, was a paper in which the Moore calculated this to leading order using completely classical methods, not the one that I showed today. And then, I mean, this observation concerning the supertranslation frame was in particular pointed out in a paper by Veneziano and Wilkowicki, and there have been also works on sort of trying to understand this by redefining appropriately the angular momentum. Also, Filippo's work on that, and papers by Porrati and collaborators, Filippo and collaborators, also Massimiliano and others. So I think it's fair to say that it's a bit of an open story yet. It's not, correct me if I'm wrong, but it's not entirely clear whether everybody has reached a consensus.
I don't know.
Okay, so if the experts don't know, I can claim that I don't know.
But certainly it's not, you can, I mean, you can write it in a way that show that it's not something that you can remove by gauge transformation.
Exactly. You can,
This piece, you can write it as a super translation invariant way.
Exactly. You sort of have to change the starting point, though, right? So instead of plugging in the standard formula for the angular momentum, whatever that means, you have to come up with a better definition of angular momentum, which makes this manifestly super translation invariant. But then there are different proposals, as far as I understand, right? There's more recent papers like Porrati, where
Well, I think at the end, Porrati boils down to
okay,
I see. With a better prescription for L equals 0, 1.
Ah, right. Because then there is this issue of separating the true super translations from the standard translations. Right?
Exactly. This is another stuff. Yes. Yeah. Okay.
Yeah. No. I mean,
too much on to details, I think.
Yeah.
Do any of these shine any light on what's going on in electromagnetism? Where there's the same problem with no super.
So formally, this derivation I presented works also in exactly the same in electromagnetism. And in fact, even in N=8, you use also for the scalar, and then you combine everything.
In electromagnetism, there's no super translation. Okay.
No, there are exactly no. For this one, there are these U1 large gauge transformations that I was mentioning.
Make change the angular momentum. That's gating variant.
I know, but I think essentially you can play the same game, because also this time it's really, I think, related to the. So my impression is the following: that this puzzle of the angular momentum is really related to these inhomogeneous shifts, which are in a sense pure gauge, in the same way as it is related here, with this piece dA, dB, etc. Instead, the issue at sub-leading order is probably related to a bona fide super translation. The homogeneous part. So I think these are a bit different issues. Somehow the two pieces of the super translation that I probably already raised, of course, is matter for these two puzzles in a different way. Though, yeah, I think we don't still have computational control on the angular momentum at the order in which the other subtlety would kick in, which is also interesting.
How one should then interpret the result?
Yeah, so my interpretation, probably different from the one that Filippo will give, is that no, I think in the end we agree, right? This is really the physical change in angular momentum, in the sense that if you take the binary system and you look at the mechanical angular momentum, before and after the scattering, it is different, and it differs by minus this. So if you phrase the question in terms of the angular momentum of the zero frequency gravitational field, it's a bit a moot point, right? Because can you actually measure zero frequency gravitational fields? I mean, you have no detector whose band stretches up to omega equal to 0. But, for instance, at leading order, this is a very concrete prediction on the trajectories, namely that their impact parameter shrinks. So there is a sort of shift or drift of the two trajectories if they start out with some impact parameter like this. Then after the scattering, they will fly off to infinity, but with an impact parameter which is slightly shorter. Although my drawing is maybe actually slightly bigger, but so delta V should be minus 1 over P times this. So this is, I think, a concrete prediction for the world lines and physical. I mean, physical, we can track where the black hole goes and then calculate the impact parameter. So
it's funny to say there's angular momentum that's going around that you can never use to spin up a disk.
I agree. So if you can devise some Gedanken experiment even that measure this, would be interesting, probably. Yeah, it all goes back a bit to that comment. I mean, I'm a bit fixated, I apologize. The comment by Strominger in the paper by, I think, 2014, in which he was saying, adding some guidance will not change the energy, but it may change the angular momentum. Yes, and this is by how much, in a sense. But then, what are zero frequency gravitons? Yeah, I think that was all the material I had in mind to present. Thank you very much for your attention.
When I have to leave, I take the role as a teacher. Do you have questions?
So maybe a question about the measurement of memory effect. So how would it look like in practice?
Yeah, okay. In practice, it's a bit more complicated than the naive idea that I presented. As far as I understand, okay, there are two things. First is that what one, if I understand correctly, what the experimental colleagues are saying, you are not actually hoping to measure this, let's say, DC effect. So really the fact that the thing go, into a different position permanently, but rather some sort of extra bump in the frequency, right? Because I think everything is measured in frequency space, then you would be able to see this 1 over omega, but not all the way to infinity, right? So some sort of bump in the shape of the signal in frequency space. But take all this with a grain of salt, because I'm not actually involved in any of this. But another point is that, as far as I understand, for the bound systems, this linear memory effect that we discussed is not really important, precisely because it boils down to a difference between the initial and the final momenta, right? But in bound system, they almost go back to their initial, right, when they rotate around each other. Okay, they're not closed trajectories, but they almost, so it's highly suppressed. So what people measure, and which is actually enhanced due to the many cycles that the bound system experiences, is this nonlinear version of the memory effect, which is due to instead actually soft gravitons emitted by other gravitons, sorry, with non-zero, or I mean, with large frequency as well. So yeah, these are only the two comments that I have.
In principle, one would
one would look at the process in a band of frequencies, and in the frequency spectra, in principle, this is observable.
No, okay, it has not been observed so far, so
I mean,
with an
in
asterisk.
principle.
Yes, in fact, there was a nice workshop in Queen Mary last June, and I think all the slides, also by people really discussing this more detailed prospects for experiments, are all online, so I can send you the link if you want. And this is a cheap way out, I know, because I should be able to reproduce their arguments instead of redirecting the links, but the best I can do right now.
I think they hope to measure it by stacking a lot of.
Yes, there is also this statistical idea, yeah, statistical accumulation of. Right, yeah, that was also an important point.
If it's this nonlinear version, it's not actually connected to softness.
It is, in the sense that they are soft gravitons, but they are emitted by hard gravitons, in a sense.
Other questions? Okay, if not, let us thank Carlo again.